Hello and welcome to our Orca3D Marine CFD webinar. We're really pleased to have such a great turnout today. It's clear that the topic of affordable, practical CFD is of great interest to a lot of naval architects. My name is Bruce Hayes and I'm a naval architect with Orca3D. I'm joined today by Larry Liebman, naval architect and lead developer for Orca3D. In addition, we have Dr. Cheng-Jae Wang and Rich Moore from Simerics, our partner in the development of the Marine CFD software. And we're very grateful to have Joe Snodgrass and David Wilson of Viking Yachts with us today. Viking Yachts was an early adopter of our Marine CFD tool. And later in the presentation, Joe will talk about their decision to adopt our software and their experience with it so far. Again, thank you for joining us. I think you're going to like what you see today, a cost-effective, easy-to-use, and reliable CFD implementation that integrates very nicely with Rhino and Orca3D. With that, I'll turn things over to Larry Liebman to get the presentation started. Larry?
Thanks, Bruce, for that introduction, and welcome again to everyone to the Orca3D Marine CFD webinar. During the webinar, we'll cover the items that we see here in the agenda. We expect it to last about an hour, and as Bruce noted, it is being recorded in case there's something you would like to review later or to show to a colleague. So I'll start off the webinar with a live demonstration of Orca Marine CFD to show you how to start a resistance analysis of a sample planing hull. This will show how easy it is to start up a simulation, even for the non-expert. We'll come back to that simulation later in the webinar to see how quickly the analysis runs. After we start the resistance simulation, we'll return to the slide presentation to give you an overview of Orca3D Marine CFD. We'll describe the primary goals for the tool and how Rhino, Orca, and Simerics work together seamlessly to meet those goals. Of course, performing high-fidelity analysis using CFD is only useful if you can trust the results. Dr. Cheng-Jae Wang from Simerics is here with us, and he's conducted a number of benchmark runs on a wide range of hull form types. He'll discuss the results of those benchmark studies later in the presentation. And in addition, as Bruce mentioned, we're happy to have Joe Snodgrass and David Wilson from Viking Yachts with us to discuss why they chose Orca3D Marine CFD and how they're using it in their design and engineering efforts. Next, we'll move on to discuss some frequently asked questions about Orca3D Marine CFD. Of course, you're welcome to ask any additional questions, and we'll do our best to either answer them at the conclusion of the webinar or in an email follow-up to the webinar participants. Then Bruce will wrap up the webinar with a discussion of product pricing and questions and answers as time permits. So with that, let's get started with our first demonstration just to show you how easy it is to set up and run a CFD simulation. For the demonstration, we're going to use a vessel called the Eastport 32 planing hull, which is built here in Maryland. Our thanks go out to Mick Price and Tom Weaver of Eastport Yacht Company for providing us with this Rhino model. So the process of performing a CFD analysis with Orca Marine CFD starts by running the CFD command, which is under the speed power menu. We're called Marine CFD analysis. The first thing they ask you is what portions or surfaces in your model you want to analyze, and I'm going to select this model here, which is a closed solid. It's important to note that the geometry must be closed in Rhino, but you can analyze multiple closed volumes. So if I had appendages that weren't part of this model, or if I was analyzing a multi-hull where the cross structure hadn't been defined yet in the model, you could select multiple closed volumes. After you select the geometry, you're given the input dialog for Orca Marine CFD, and the information is quite straightforward, especially to those of you who may be using Orca already. First, we're going to specify the mass properties of the vessel. I'm going to enter a displacement of 10,000 pounds, longitudinal center of gravity of 17.8 feet from the origin in Rhino, and a vertical center of gravity of 3.35 feet. So that defines the mass properties. I'm going to click the float button, and what that does is calculate the sinkage, trim, and heel values of the model for those mass properties in order to figure out what the static equilibrium position of the model is. this is useful because it's used to initialize or set the initial conditions over in the CFD analysis. As far as moments of inertia, which are important for a dynamic analysis like this, I'm going to stick with the rules of thumb, namely the pitch gyre radius, for example, being 25% of the length of the vessel. We'll talk a little bit more about this later in another demo. Down in the Simerics analysis tab, we have the name of your project, the path to where you want the files to be created and run in Simerics, the type of hull that you're analyzing for the meshing template. This is clearly a planing hull. You can see we have three options: displacement, planing, and high-speed displacement. Whether you're doing a resistance or a powering, or also called self-propelled run, we'll stick with the resistance run for right now. The speed or speeds at which you want to perform the simulation, I'm going to say 25 knots for this simulation. You can override your fluid properties. They were set in another place of the user interface because we chose seawater for this model. But if you want to override those density and viscosity values, you can do that. And lastly, I'm going to go ahead and apply some attributes to faces to help the CFD analysis, and particularly to help in the post-processing side. Here I can choose one of three types of face attributes: hull, deck, and transom. And you can see by default everything is set to hull. What I'm going to do is choose the surfaces on the deck and make them deck surfaces, and then lastly apply transom attributes to the faces on the transom. And you'll see when we get into the CFD side of the problem how these face attributes are used. Once you have that done, you're really ready to go. You click on the Run Simulation button, and it asks you what simulation you want to run, because I could have put in multiple speeds there, but you can see the one that I just created for 25 knots, and I'll click on Launch, and that starts up the Simerics MP user interface that you see here. And what the interface, what is happening right now, and we'll talk a little bit about this more later, is the marine template that's built in to Orca Marine CFD is setting up the CFD problem. It's automatically creating a CFD grid. It's creating or setting values, parameter values for things like the solvers that are being used, the time step to use, the length of the simulation, and other factors as well. So you can see in a matter of about 30 seconds, I have the CFD simulation set up. There's two graphical views here. I'm going to zoom into this one view. You can see there's my model. Note one item I didn't mention on the model when we were back in Rhino is that there's a fair bit of detail in this model in terms of the appendages. The model has rudders, shafts, struts, spray rails. There's a rubber rail a little bit above the waterline. And this model also has superstructure modeled. That is entirely up to you whether you want to include that kind of detail in your analysis. In this particular analysis, we're interested in the flow in the air as well as the flow in water, so we chose to include that in the model, but that's entirely up to you for your particular analysis. So a fair bit of detail here, and really all you need to do is come into the simulation tab. You'll notice things like the number of iterations and number of time steps are set up for you already, and all you have to do is click the Start button. It asks me if you want to save the current setup. I'm going to say yes, and it's going to save the grid, and the simulation is going to start. So it's a very simple process, straightforward process, doesn't require a lot of CFD expertise, and I'll talk to why that is in a moment. We're going to let this simulation run in the background while we go back to the slide presentation, and we'll come back to it later just to see where things are and show you a little bit around the CFD interface and what kinds of information you can glean from the simulation. Okay. Okay, so while that CFD simulation is running, let's talk a little bit about the goals, the design, and the capabilities of Orca Marine CFD. You know, computational fluid dynamics tools have been available for many years, but the technology has generally been very expensive and limited to use by technical experts having much greater computational power than the typical design office has. The primary goal then of Orca Marine CFD is to bring this proven technology to the non-expert, that is the naval architect or the marine engineer who needs high fidelity analysis to make important design decisions. Specific goals of Orca CFD include the ability to evaluate hydrodynamic and aerodynamic performance of any hull type and the effects of unique design features that are not readily captured by empirical techniques. You know, for many years, naval architects have been predicting hydrodynamic performance of designs using a combination of our own experience, rules of thumb, and empirical prediction techniques. In fact, Orca3D includes two semi-empirical drag estimation methods, one for planing hulls and the other for displacement hulls. However, modern designs almost invariably incorporate features that weren't accounted for in the empirical method. For example, hull steps are very commonly seen today on the bottom surfaces of planing hulls. In addition, multi-hull designs have become popular in many segments of the marine industry. And while there are some empirical methods available for multi-hull designs, the applicability of these methods becomes limited when your design's characteristics go beyond the method's parameter ranges. Orca3D Marine CFD then allows you to evaluate both the hydrodynamic and aerodynamic effects of specific design features and design types using a first principles approach. Another goal has to do with model testing. Model tests have long been the gold standard for hydrodynamic performance analysis, but they're typically expensive and very time-consuming. In addition, scale effects can be significant for certain flow phenomena. CFD allows you to perform full-scale evaluations, so you don't have to worry about scale effects. Orca CFD then helps you to minimize or potentially avoid the expense and time associated with model scale test programs. Another goal of Orca Marine CFD was to help you or help the designer perform high fidelity evaluations in earlier stages of design when the decisions have the largest impact. Things like being able to improve the performance of a design through parametric studies of hull shape, center of gravity location, hull spacing, trim tab settings, and many other variables in the design allows you to come up with the optimal design parameters. And finally, the ability to discover and avoid potentially costly design flaws before the design is even built is a major goal of Orca Marine CFD. Okay, so what is Orca Marine CFD? It's an integration between Rhinoceros, the Orca3D Marine plugin for Rhino, and the CFD application called Simerics MP. Some of you attending the webinar already use or are familiar with Orca3D, which adds marine-specific design and analysis functionality to the general-purpose Rhino modeling tool. Orca CFD adds functionality to leverage much of the design information that you already have in your Rhino model for CFD analysis. It's important to note here that the inclusion of Orca3D in the architecture does not place any specific restrictions on the Rhino model that's used. Orca3D works with virtually any Rhino geometry model, even if it was created without Orca or in another CAD tool for that matter. For those of you who might not be familiar with Simerics, Simerics MP is a full-featured, multi-purpose RANS CFD tool. It has all of the capabilities of other general-purpose CFD tools that you might be familiar with. As integrated with Rhino and Orca3D, it includes those CFD modules commonly needed for analysis of marine problems, for example, the fluid flow, multi-phase, turbulence, dynamics, and the other modules that you see listed here. Simerics MP offers several advantages over other CFD tools, including a very fast and robust solver that allows you to run your simulations on a typical desktop or laptop like I'm running here. It also includes an automatic mesh generator to facilitate the fast and easy generation of high-quality CFD grids, and we'll talk about that in a moment, as well as efficient setup of CFD simulations for specific domains through this specific domain-specific template architecture. So what is the template architecture? The template architecture allows you to set up CFD simulations for very specific problem types using only a little bit or a modest amount of input. The marine template that is used in Orca3D Marine CFD incorporates the technical expertise of the CFD analyst, thereby allowing the non-expert to effectively apply CFD to marine problems. In short, Orca3D Marine CFD leverages your Rhino design to facilitate high-fidelity CFD resistance and powering analysis. So what are the capabilities of Orca Marine CFD? What can we do with it? Well, in order to make this approach that we're using as robust as possible, Orca CFD is focused on those analyses that are most commonly needed by the naval architect, specifically calm water resistance and self-propelled analyses. As you can see here, we can analyze both displacement hulls and planing hulls, mono hulls, and multi-hulls. So in the graphic on the right, you see a catamaran running, and in this particular analysis, the effect of hull separation was being studied. Features such as appendages, hull steps, trim tabs, tunnels, foils can all be analyzed, including heave and pitch prediction, as you see in the graphic on the right. And Chen-Jay will show you a little bit later a study of planing boat porpoising instability, so that can be clearly identified as well. You can look at streamlines both in air and in water, and for asymmetric simulations like the one shown at the bottom with a sailboat hull at a yaw angle, you can measure things like side forces and moments. And lastly, wake studies, again as shown in the bottom left, you can analyze inflow into your propeller for wake analysis. So these are all examples of types of things and analysis you can perform with Orca Marine CFD. Now that you know what it is and what it can do, let's discuss how it works. Orca CFD lets designers use their normal workflow by creating their designs in Rhino using the native Rhino modeling capabilities, and optionally the marine-specific design and analysis tools built into Orca3D. Once a design is ready for CFD analysis, Orca CFD allows you to seamlessly transfer the design information over to Simerics MP for analysis and post-processing. Information that's transferred includes mesh geometry, mass and fluid properties of the model, and the static equilibrium attitude defining the initial condition of the simulation. We also account for whatever unit system and model orientation you're using in Orca3D and Rhino. If you're running a self-propelled model, the propulsor information is transferred. And finally, some Simerics specific analysis information, such as whether the model represents a planing hull or displacement hull, is chosen. Once in Simerics MP, the model is all set up and ready to run. All that is left to do is to start the simulation and view the results. Now that we've shown you a little bit about Orca Marine CFD is and how it works, let's move back onto the next demonstration, which will show you how to set up a self-propelled analysis. And then we'll go back to the simulation we had started earlier today and see how it's coming along. So I'm going to go back to my Rhino model here and talk about how you would set up a self-propelled analysis. Really, all of the information is the same there. The static equilibrium condition is the same. The mass properties are the same. I should note that when defining the mass properties and static equilibrium condition, you have a choice of either specifying the weight and center and floating the model to figure out your orientation, or specifying your orientation and floating the model to figure out your displacement and center of gravity. So either option is available there. Okay. The thing that's new when we're going to do a self-propelled analysis is now we change our analysis type to a powering run. And as soon as we do that, we get a new tab, which is where we define our propulsors for the model. I'm going to click the propulsors tab and add a new propulsor. And you can see I have the information to fill out for the new propulsor, which includes its geometry as well as its performance. I'm going to say it's a right-handed propeller, a diameter of 1.5 feet, with a hub diameter of 1/4 of a foot, thickness of 0.3 feet. And while I can type in my location and angles to baseline, I can also use Rhino's capability to place the model, place the propeller using the snapping capabilities. So I'm going to come in here to the end of the, and click on location and click on the end. And you can see I placed it right at the end of the shaft, and then I'm going to go into a profile view and click on the direction option and just set the direction to be along the direction of the shaft. Once I've done that, I come back and it's figured out my location and angle for me. And then I have to define the performance of the propeller. How much thrust does it generate and how much torque does it absorb? So there's a couple of different ways of defining the propeller performance. If you have open water thrust and torque coefficients, you can enter those in here as a function of advanced coefficient. More typically, you may be able to define an equivalent B-series prop, and we will figure out the open water performance for you. So for a B-series prop, you might only know things like the number of blades, 5 blades, the expanded area ratio of the propeller, and the pitch to diameter ratio. And that is enough information to automatically generate a B-series open water curve. Lastly, we have to enter the propulsor force time profile. In other words, what RPM is this propulsor going to operate at? And you can choose a fixed RPM where it's fixed from start to end of the simulation, or you can choose a linear RPM ramp where you specify a target RPM, say 1600 RPM, or I'll say 1650, and it ramps up over 5 seconds. Okay, once you've defined that, that's all there is. The rest of the simulation input stays the same, and all you would need to do there is click the Run Simulation button, and you'll get a new simulation created for you, and it's going to go through the meshing process, automatic meshing process, just like it did last time. Everything will be the same, except the one thing that'll be new in the simulation is it'll have a propulsor driving the force. In the resistance run that we did earlier, you can think of that as a towed simulation. The target velocity will automatically be reached, and as much force as necessary will be produced to generate that target velocity. Whereas in a self-propelled run, you only have the propulsive forces accelerating the vessel, so it takes typically longer to get up to the speed of the analysis. Okay. So in a minute here, it'll finish meshing and we'll see the same model, but with propulsors in it. Okay. All right. So let's go back. This was the self-propelled run. Let's go back to the run that we started a little bit ago at the beginning of the presentation, and let's examine where we are and how far we've gotten in the simulation. Okay. So the first thing I want to emphasize here is there's a module. These are the modules in the simulation. There's something called a marine module. When I click on that, you can see information that was imported from Orca3D and Rhino, namely things like the mass of displacement of the body, the moments of inertia, fluid properties, center of gravity, the orientation of your model. All of these were imported directly from your Rhino model. So that's a big part of what the template does. You see I have a three-dimensional view, graphical view, where I can zoom in and look at various aspects of the model. I can look at the mesh that came in from the model. So for example, I'm going to turn on the symmetry plane, which is the plane that defines the domain transversely, port and starboard. Since it's a symmetric model, we only need to run half of it. And if I look at that view and turn on the grid, you can see that the marine template automatically created a mesh that was suitable for this type of a hull. It's placed higher density mesh values, or smaller mesh cells, I should say, closer to the hull and in the area in the vicinity of the free surface in the wake. In a similar way, if I look at the free surface model from the top and turn on the mesh, you can see it's created a mesh that's, again, suitable for something that's operating on a free surface with angles of the mesh matching more or less the Kelvin wave angles coming from away from the hull. So part of the marine template is the knowledge and expertise of how to create this mesh for you automatically. Okay. You can create as many different views, three-dimensional views of the model as you want. So in addition to this view here that we're looking at with the free surface and the hull, there's another view where we're looking at what we call volume fraction. Volume fraction is the fraction of each cell that is water or air. So in this case, you can see purple represents portions of the model that are water, blue is the air, and anything in between is mixtures of air and water in the cells. Okay, and you can create as many views as you want. All right. Another useful feature and way to monitor the simulation is to create two-dimensional plots. So I'm going to create a 2D plot here down at the bottom, and what I'm going to show in that plot are a couple of things. First, I'm going to show heave and pitch values, so you can see how the vessel is heaving and pitching as time moves on. Clearly, when you're looking for a converged result from your simulation, you're looking for these values, these channels of data, to level out to more or less constant values. I can also create a plot of total resistance, okay? And the reason you see this spikiness in the resistance up until 0.1 second is because the way this simulation works is it accelerates the vessel to speed. I can show this if I plot the speed on the same axis for velocity. It accelerates the speed, you can see with the red line, up to your target speed in 1/10 of a second, and then it holds it constant. So the towing carriage is accelerating and then holding a constant speed, so to speak. And now we're waiting for the transients to reach a to die out and reach a steady state in terms of resistance and heave and trim. Okay. How do you get this data out of the plot? Say I want to see these resistance values numerically. There's an option here to copy the data to the clipboard, and then by starting up your Excel workbook and pasting that data, you can get the time-dependent values out of the simulation. And I should note you can use any unit system that you like. So you can change units here. If instead of newtons I want to use pounds for the force, you can change it to pounds, and it'll apply it that way, and it'll come out in pounds. Okay. So this simulation will continue to run. Let me go to this other simulation here, close this, and let me open a simulation that was completed for this case, for the 25 knot case, while this one's still running. And one of the neat things that you can do with Orca Marine CFD and Simerics MP is you can load results from a prior run. So I'm going to click the load results button and scroll down here and load up the results from a prior run of this simulation. Now you notice this one didn't have the superstructure, but that again is a decision that needs to be made by the designer. So when I load results in here, you'll see that those plots of things like heave and pitch have started to reach a more or less constant level. Likewise, resistance has as well. Okay, and the other thing I just wanted to show you real quickly is we get sometimes people asking about streamlines. Can I show streamlines in my model? And of course you can. The simple thing to do is add your streamline module to your simulation, turn on streamlines for your surfaces. So I'm going to say, yes, I want to release particles for my streamlines. I'm going to set the size of my streamlines so they're not so large. And I'm going to associate a variable with them, which will make them animated. So I'll use a velocity magnitude. And so you can easily define streamlines as well as the free surface in your model and look at the flow effects of those streamlines. Obviously with the top side superstructure, the flow might have been a little more interesting up in the air, but you can get a lot of useful information for flow around appendages and things like that. Okay. Okay, so with those demonstrations, let's move on to a common question that we get, which is, how can I have confidence in my results? People see that you can get nice images, animations from simulations, like the ones I just showed you, but they feel like they really don't know much about CFD analysis, and they aren't sure they should trust the tool or trust themselves to use the tool properly. Well, first, as I mentioned earlier, the template architecture used in Simerics MP was designed from the outset to incorporate the technical expertise required to achieve reliable results. So things like the CFD grid arrangement and density, the numerical solver settings, the time steps for your simulation, and other simulation parameters are automatically defined for your specific model and analysis. I should note that these simulation parameters can be changed in Simerics MP if you want to do something beyond the typical analysis, like you want to refine the grid around a specific area of interest. Of course, in order to be sure that the implementation of the physical models used in Simerics MP are robust, numerous benchmarks have been run against known measured data for a wide range of designs. And Chen-Jay will describe the results of the benchmarking process, which is ongoing even today. And finally, we'll also hear some comments from Joe Snodgrass and Dave Wilson at Viking Yachts, who have found that they can use Orca Marine CFD to address a variety of problems. So with that, I'm going to give control over to Dr. Chen-Jay Wang to continue with discussion of the benchmark analyses he's performed. Chen-Jay?
Thank you, Larry. So, thank you, everyone. So, for the next couple of slides, I'm going to show some benchmark problems we have done through the Orca3D Marine CFD. So, the first example I'm showing here is for a planning hull. A systematic experiment was done in 1960s for this kind of planning hull. It was done for different displacement, center of gravity location, different ship length, and the triangle. And for the comparison, we are comparing the resistance, sinkage, and the trim. As you see, for one setting, we have very good agreement for a large speed range. As you see, we follow the resistance very well. We capture the high trim very well. And this is how the flow field looks like. And moreover, for this big systematic experiment, we also done different simulation for that. And all those results has been presented in the Tsunami Maritime Convention in 2017. And you may find a paper over there for this particular hull. This is a tow tank test. And for the next one, it will be a self-propelled planning hull. This is one of our client example. So what he wants to get is he wants to just provide us a propeller RPM and want to determine what's the flow condition and most importantly, whether it can meet its final maximum velocity requirements. And by doing the simulation, the propeller are properly modeled. The acceleration is well simulated. He do see how we get to the planning period through a pouring period, which means you have really high trim angle. And also the boat motion is accurately captured. And moreover, is based on their sea travel data, our final velocity prediction is within 1 miles per hour difference. So they are really amazed by that. And also by doing the CFD, you can see more detailed flow features around the appendage, for example, around the outboard engine. The next example is also on the planning hull, but this is on a different thing is the porpoising, which is the natural instability. So here I'm just going to show you an example of how the CFD can help you to define those kind of design flaws in a very early stage. Basically, there are two identical hull shapes, but we just put the center of gravity in different locations. Let's see what happens if we have it run. So as you see, when the center of gravity is properly placed, the hull just go on the planning mode and stay there. But for the one which is being wrongly positioned, we see the hull starts porpoising and it can never recover itself. So that's just show you how the CFD can help you to identify those design flaws in a very early stage. The next one, we move our planning hull to a Catamaran. So it's a high-speed multi-hull. Also, we compare our simulation results with experiments on the resistance, sinkage, and the trim. as you see, the simulation successfully captured the effect of a different spacing. And if we see from the bow area, here is the waving action, as you see. For a narrow gap and for a wide gap, you see there is a really big difference there, and they will ultimately affect the resistance, sinkage, and trim. Our next example is a sailboat. It's worth noting that when we are doing this simulation, it is a blind test. But as always, we got very good comparison with experiment, even though we don't know any of those experiments before we run in the simulation. Here is how the wave looks like from the bow area. So the next one, we go to a little bit bigger, the displacement hull. I think a lot of your people have known this hull, DTMB hull is quite famous. And as always, we got really good comparison on the drag, sinkage, and trim over a large speed range. They all agree very well. And moreover, for this toe tank test, we can also compare the wave shape on the hull. So here is the comparison. As we see, they meet very well with the experiments. Also, we can test the flow field around the hull. Here is the wave cut comparison at different locations. We do have a very good VOF solver. That's how you can get this good agreement with experiment in the wave shape around the hulls. The next hull is also a displacement hull, but we'll make it a little bigger. It's a big container ship. It runs a little slower, so the flow number ranges from 0.1 to 0.3. But as always, we got excellent agreement with experiment and also on the wave shape around hull. As you see, even though we have a bobber spool, we still got everything very well. The next example, still displacement hull, but we make it even bigger and a little bit slower. It's a really big tanker. For the flow number, which is less than 0.2. As you see, here's the two examples. One is a KBL CC2, the other is JBC. As you see, very good comparison with experiments. And this is how the wave field looks like from the bow area. So as a quick summary, as you see, we got excellent agreement with experiment data and sea trial data for different types of hull form. For example, the planning, displacement, catamaran, sailboat. And also I want to point out this is just a small portion of the benchmarks we have done. We have a lot of other data. Some is public. It's kind of similar to what we have shown here. The other ones is kind of a proprietary data we are comparing with. And also, as you know, Simerics itself is a general purpose CFD. We not only doing the benchmark inside the marine industry, we also do that outside marine industry in other fields as well. And basically, we are still working on that. And Orca3D and us, we have grouped up as a great team, and we are benchmarking more public and custom hull design to improve our solver and the default settings to help you. Some of you are really have a lot of expertise in the CFD. Some of you probably don't know too much, but we will back up you no matter what kind of expertise you have. We want you using our software to have the best results you can get. And thank you. I'll hand back to Larry.
Thank you, Chen Jay. That was excellent. And now to continue to answer the question of how we can have confidence in our results, we want to invite Joe Snodgrass and David Wilson from Viking Yachts to talk a little bit about some internal benchmarking they've done and a little bit about their experience with using the tool. So Joe, David?
Good day, everyone.
Good morning.
Well, David and I have been talking about CFD for at least over 12 years. You know, and in our first discussions, the software was just way too expensive, and the the CPU power that was required was just out of our reach. So it was something that we knew existed, but was just kind of not something that was available to us at the time. So what we've always been doing is that we always tank test. So we were looking for a way to improve on our options of tank testing. Tank testing, a lot of it had to depend on the schedule of the tank and the tank's availability. And then it came down to the amount of time they had available. If we were to go to the tank for a week, you only can get a certain amount of runs in per week. And you need to get a certain amount of runs to make each study worth it. So that limited the amount of variations that you could have, with the hulls. So we considered using some outside CFD analysis resources a few years ago. We had approached a few companies. They needed us to send them the models, but the models needed a lot of pre-processing work. They weren't cleaned up enough to be closed single poly surfaces. So there was some extra time involved. I think our expectations may have been too great at the time, and we just always seemed to run out of time. So we didn't have much luck with using outside CFD resources. And then part of that could have just been on us as well. But and then as the software continued to evolve and the computers became more powerful, things started looking like they were more in reach. Maybe $100,000 or something like that for the total package. But what we also started realizing was we were going to need an expert to run the software. We were going to need to hire like Cheng-Jae. And that we would need to use the software would need to be running all the time to make all of that cost worth it. So again, we kind of found ourselves not quite there yet. And we just continued with the tank testing. Then I guess it was January of last year, we use Orca every day, Orca and Rhino. So I noticed that in the speed analysis that there was the Marine CFD analysis, and that was new. So I was like, oh, neat, let me check this out. So I started clicking on the buttons and following the instructions, and I used the hull wizard, created a simple hull. I selected deck, transom, and hull, and was about ready. I tried to run the analysis, but it told me I was missing an executable file. So I sent an email to the Orca guys, and they told me that you had to pay for that. And that essentially started the ball rolling. I showed David what was now available and through Orca, so that really that sparked our interest. And we started the conversations with Larry and Bruce, and we discussed with them that what we had done a few years back with some of the guys from Stevens, Michael Morbido, who now works at the Naval Academy, we did a paper at the Chesapeake Powerboat Symposium that compared full-scale sea trials to tank testing and how well we were able to have them overlay. So one of our 82 convertible story was that we took tank test models up to Stevens and ran them and we were unhappy with the results we got. We did not have the hull wasn't finished yet. So we had time to make testing. So then we had the Orca guys, they were showing us how well this software would correlate with full scale and the tank test. So so David and I at that point were sold. We were sold on the software, but we had to figure out how to approach our bosses to acquire the software and how to make it worth it. So Patrick, the owner of the company, he was quickly on board. He saw some of the marketing benefits through some of the screenshots and the animations that are able to be created. And then Lonnie, the vice president of engineering, he was very concerned about time and how much time we would use on the software that would not be used to what we're normally doing during the day. So we had a bit of we had to prove it to everyone to show them that it was going to be worth it. So we got the software. We went down for some training in August that was very helpful, and off we went. I mean, David and I from day one had talked about what we thought was going to be a very simple approach to our design process. Like early on, we start a new project and we have a hull. And we have some basic hull parameters where we know the size the boat needs to be. It can't be any longer than X feet. And based on that, we have a pretty good idea of the gross shape. But we could we wanted to be able to make 3 or 4 or 5 different variations and just run them and compare them all to each other. And as simple as that, just looking at which models were producing the least resistance, the least amount of effective horsepower required for speeds, and then just start following that direction with the new designs for the hull shapes. So that goes along with the resistance runs, which are what we feel are very similar to like the tank testing. But when we came back from training, we quickly found ourselves with a new boat that wasn't running quite the way we wanted to. So we modeled that with all of the appendages, and we started doing the powered runs. So I kind of felt like that I started in the deep end of the pool when the intentions were to start at the shallow end of the pool. But we've been very impressed with the software and what we've been seeing. Hey, Larry, can you go to the next slide? So here, those 4 shots on the right are underwater photos from the tank. And each one of those models is slightly different. So in order to do that at the tank, that requires physically changing the models on the carriage, and it takes time, where in Rhino, all you need to be able to do is just model those changes. And if you have 4 different models like that, well, now we can run them in CFD. And we're getting very similar looking results. On the animation on the left is showing similar stagnation lines. I think these are similar conditions, but they might not be exactly the same conditions, but it is showing very, very similar. Let's see. So one of the things that's also we weren't really expecting was some of the additional uses of the software that we thought that we might be able to use farther down the road, looking at some of the flow. But one of the things that we did start looking at before the holidays were our engine pickups. And we ran 6 different shapes of engine pickups, and it was interesting to see the difference between the resistance on the shapes. So and the flow, how that was all working. So, and then early last year, we did a cockpit extension on a hull, and we had trouble initially with that hull getting up on plane because the cockpit extension was acting like a step, and we had not ventilated the extension. So we did a lot of full-scale testing to finally, to solve the problem and the boat gets up on plane. But our thought is, had we had the software in hand at the time, we could have greatly reduced the amount of time that we spent on the full-scale testing. We might have been able to go from 12 different design iterations maybe down to 2 or 3 before we finally had it all going the way we wanted. I think those were sort of the big points. Did you guys, Larry or Bruce, was there anything else you guys wanted us to sort of head towards?
Nope, I think that was the predominance, and we certainly appreciate your input. We as developers have our thoughts and ideas about the tool, but having feedback from customers like yourself who are actually using it, I think, is invaluable. And also, we really appreciate, the feedback you've given us about the tool, things we can make the tool better, ways we can make the tool better, and ways that it's being used that we didn't even envision. So thank you very much for that. And I think between the benchmarking and the types of projects you've been using the tool on, as well as what Chen Jay showed, both of those really, I think, help us and help the end users understand how they can be confident in the results they're getting out of the tool. So thank you very much for that, Joe.
Sure.
Absolutely. Larry and Bruce, if I could just add one more thing that really hit me in the beginning of Joe's explanation of our early considerations of the software. There's times that I know other companies here listening in can appreciate the time in the market in the marine industry in regards to their specific budget that has certainly affected the Viking Yacht Company, that I can tell you tank testing was unattainable, mainly due obviously to the costs and the time required. And when you combine the time required for tank testing and the people out of the office required to be there, and then the budget itself, again, I really want to emphasize that I'm sure some other people listening in can appreciate that tank testing was not attainable for us. And as a design department, especially internal, as we are lucky to have here at our facility, it was unfortunate for us. We would like to be tank testing constantly throughout the entire year, model after model after model. And that, even in good times, is not attainable. Now, with this software in-house and really making the investment comparatively to tank testing in some ways, it really puts the tool in our hand very positively. So, I could speak in more detail and more specifics to that. And we've discussed that with you gentlemen, which you can share. But I think you guys understand as well as we do, it's not even comparable when you have those moments that now that we've made the investment this year in the software, the investment's been made, it's in our hands, and it's now, it doesn't need to be looked at by our upper brass to say, oh boy, gentlemen, next month we really can't afford to go to tank testing. So it's taken that off the table for us, and now it's in our hands, and that's it's quite invaluable immediately, and it's amazing to see it when we look at simple little, besides resistance and hull form, looking at little jobs like engine intakes, flow characteristics, ventilation issues if we have a specific model with a cockpit addition. So that's it's duly noted, and it becomes invaluable there once you've made that investment. And we did not see that forthcoming until we dove into it. And I really want to commend the software and you gentlemen at Orca, bringing all that to light to us.
Well, thank you very much for that, David. Yes, and it's been certainly a pleasure from our side to work with you and see ways that we didn't even envision the product being used. So I think it's been a great partnership. Okay, so let's move on to the next discussion. We're coming towards the end of the webinar here. There's a few topics to cover. And this next topic has to do with frequently asked questions. These are some common questions that we often get about Orca Marine CFD that we want to try to answer here. But as Bruce noted earlier, we certainly encourage you to ask any other questions that you may have. And if we can't answer them here during the webinar, we'll put our heads together and come up with what we hope are good answers to the questions and send those all out to you as a follow-up to the webinar. So one of the first questions that I think we get, and I'm sure many of you have on your mind already, is how long does it take to run a simulation and what kind of hardware is required? And one of the strong points of Orca Marine CFD is it doesn't require a dedicated cluster of computers to run. It'll run on virtually any contemporary desktop or laptop computer. As sort of a recommended hardware guideline, we might advise you to get maybe 16 gigabytes of RAM memory. The RAM isn't a big problem because most of the models we run are on the order of somewhere between 2 and 5 million cells, and our experience has been that there's a rough correlation of 1 million cells to a gigabyte of memory. So 16 gigabytes should generally be enough to run most simulations. And then you want a reasonably fast multi-core processor, because the tool will distribute its load on as many as 8 cores on a single computer. So I have the laptop I'm running here is a Lenovo laptop with a quad-core i7 processor. I think it's not untypical of a contemporary engineering computer, and sort of a rough time frame or time information for the runs I've been doing. For this run that I'm running now is in the demo. It's about a 2.5 million cell model, and obviously it's a planing hull, and at a 25 knot speed it takes about 4 to 5 hours to complete. Displacement hulls tend to run significantly faster, having to do with time steps and mesh sizes, and so a single speed for a similar size model of displacement hull may take on the order of 2 to 4 hours to run on my Lenovo laptop. For the self-propelled runs, it's difficult to make generalizations about the time it takes because there's more variables. It certainly takes longer than the resistance runs, because rather than artificially accelerating the model up to the target speed, you're letting the propulsor accelerate the model. But there are also other more variables. In my specific case for this Eastport 32 planing hull, it took about 8 to 10 hours. For the 25 knot case, it was a 1600 RPM run to complete. So that gives you sort of an idea of the hardware you need and the times that it takes, just depending on the nature of the simulation. Next question is, can I run multiple simulations in sequence automatically? So maybe you're doing an analysis over the weekend and you're going to let the computer run, but you don't want to have to stop and start simulations for different speeds, for example. And the answers to that is yes. We can provide you with a script that will allow you to run a series of simulations, say across a speed range sequentially. So when one simulation stops, the next one runs. So why do I need both the Orca3D plugin and the Simerics CFD? I have Rhino already. Can't I just get Simerics CFD? And what does the Orca3D plugin offer me? Well, hopefully what we've showed you during the webinar is that Orca3D makes the analysis, the CFD analysis, straightforward, and it also minimizes the likelihood of error when transferring your data. Orca provides a straightforward and familiar user interface, much like the Rhino interface, to allow you to enter much of the required input for the analysis. It also helps to set up the CAD surface meshing process with the optimal mesh parameters out of Rhino. And it provides, of course, the hydrostatics capability necessary to float the vessel to equilibrium for the initial condition. So I just want to note again, I've mentioned it earlier, that there is no requirement. It doesn't matter if Orca was used in the design of your hull model. Any Rhino model can be used as long as it follows the requirement that it's a closed volume in the CFD analysis. And lastly, I would say, if you don't have Orca, we're pretty confident that you'll find it to be useful for much more than just the CFD interface. We think the hydrostatics and stability capabilities, as well as the modeling capabilities, will be found to be very useful for you in the future. Next question is, can I apply external forces to the model? And the answer to that is yes. You can apply external forces in Simerics. There's several types. You can apply forces that are fixed to the body. So when it moves, the force vector moves kind of like propulsive forces. You can apply forces that are fixed in the inertial coordinates and the world coordinates, as well as forces that vary in a prescribed manner over time. There's expression editors built into Simerics that we would show you as part of the training to show you how to create define an expression for a variety of purposes in Simerics. Can I run simulations with yaw and heel angles? This question comes up for sailboat analysis designers a lot, but in other cases as well. And yes, you can run simulations with fixed yaw and heel angles. Right now, the degrees of freedom are pitch and heave. Yaw and heel are fixed, but you can run a fixed yaw and heel angle so that this might be useful, for example, to compute the forces and moments on a sailboat at different over a range of yaw and heel angles to generate the input data for velocity prediction programs. So you can do that with Simerics MP. And lastly, we always get the question of, can I run simulations in waves? And the answer is simulations in waves can be done in the general purpose Simerics MP tool. It is a part of its capability suite, but it's not currently part of the marine template that we use in Orca Marine CFD. And because it requires really additional training and expertise, we focused on those analyses initially that we can with confidence say will be reliable without a lot of training and expertise. So while it is in Simerics MP generally, it's not part of Orca Marine CFD. So hopefully I've been able to at least pique your interest in Orca Marine CFD during this webinar by demonstrating that it's easy to use, it's reliable, and it's fast. And now I'll go ahead and hand the presentation over to Bruce Hayes to describe what we feel is a very affordable system as well. Bruce?
Thank you, Larry, and Chang-Jae, Joe, and David for an excellent presentation. That's a lot of information to try to pack into 1 hour, but I think it's clear that Orca3D Marine CFD provides naval architects with a powerful, reliable tool that can solve a wide range of problems without the need to be a CFD specialist. And in keeping with our goal of making CFD approachable, we've also made it very affordable. The CFD pre-processing that Larry demonstrated is part of the Orca3D plugin, specifically in the Level 2 option. As Larry said, if you've created your hull model using just Rhino or even imported it from another NURB surface modeler, that's fine. You can use all of the functionality of Orca3D, such as real-time sections and hydrostatics while you edit the surface, lines, drawings, and offset tables, hydrostatics and stability calculations, parametric speed power tools such as Savitsky, and so forth. You can use all of those Orca3D capabilities on your hull model no matter where it was created. And of course, you can use it as input to the Orca3D CFD pre-processing. So if you already have Orca3D Level 2, you don't need to do anything with your Orca3D license. If you have Level 1, you'll need to upgrade it to Level 2 for $1,390. If you don't have Orca3D at all, you'll need a Level 2 license for $2,780. The license for the Orca3D plugin is perpetual, just like Rhino's license. Over on the CFD side, we have two types of licenses for the Simerics CFD module itself. First, for those of you who will use CFD on a regular basis, we have full-time licenses for either 3 months or 12 months. On the other hand, if you expect to only use it occasionally, we have something called intermittent licenses. This allows you to use the software in 1-month increments, and you can purchase either 3 1-month increments to be used within a 12-month period, or 6 1-month increments to be used within a 24-month period. For both full-time and intermittent licenses, we offer the standalone or floating network license option. And all of these licenses include an online orientation session, software updates, and technical support. Okay, so at this point, I think we're coming to the end of our time window, so we'll just collect the questions that have been entered during the webinar. We've had a number of good questions, and I'll leave the webinar open here for a few more minutes if you have additional questions that you want to type into the GoToWebinar pane. And of course, you can also send questions at any time to support@orca3d.com. Over the next few days, we'll assemble the questions that we've received and provide written answers to them in a follow-up email to all of the attendees. We won't identify the questions, it'll be anonymous. And we'll also include a link to the recording of this webinar, as well as instructions on how to request an evaluation version of the software and purchasing information if you're ready to get started. Again, feel free to contact us anytime at support@orca3d.com with any questions. And on behalf of Larry, Cheng Jae, Joe, David, and Rich, thank you very much for your time and for your interest in Orca3D Marine CFD.